So let's suppose we have a function with domain A and codomain B. If I pick any element of the codomain, we can define the preimage of that element to be the set of all elements of the domain so that f of A equals B. So specifically it's written like this. The preimage of B with this little superscript -1, which does not mean 1 over. This is not reciprocation. This is notation for preimage. The preimage of B is given by the set of all elements of the domain such that f of A equals B. Let's look at a specific example. The function f of x equals x squared, and we're declaring that the domain is integers and the codomain is integers. Okay, so now if we ask, what is f inverse of 4? What is the preimage of 4? Well, it's all solutions to f of x equals 4. In other words, x squared equals 4. There are two solutions, 2 squared equals 4 and -2 squared equals 4. So both of those things go into the set, the preimage of 4. But what if I ask the preimage of 0? There's only one integer for which x squared equals 0, and that's 0. So this preimage only has one element in it. And if we ask what's the preimage of 2, because there are no integers that satisfy x squared equals 2, there are no elements of this set, so it's the empty set. Another example, a function whose domain is all reals and whose codomain is the integers. F of x is the largest integer not larger than x. This is just rounding down to the nearest integer. So the preimage of 4 asks, what are all of the real numbers that if I round them down, the result is 4? It's going to be every real number in between 4 and 5, which does include 4 and does not include 5. 4 rounded down is still 4, but as soon as I hit the number 5, if I round that down, I'd get up to 5. So it's everything in between 4 and 5, which does include 4 and does not include 5. In fact, if you pick any integer, the preimage of that integer will simply be this interval, from the number to the number plus 1, including the number I was trying to get out, but not including the next one. If we can define a preimage of a single element B, we can also define the preimage of an entire set, any subset of the codomain. The preimage of that set is defined to be all elements of the domain which are sent to any element of B prime, the set we were taking a preimage of. This happens to also be the union over every element of this set B prime of the preimage of that single element which we've already defined. So it's really just, if I want to take the preimage of a set, I take the preimage of every single element in that set and then union them all together. Now on to a term, injectivity. A function is called injective if, given any two elements of the domain, if they happen to be equal in the codomain, when I send them through the function f, then they were in fact the same element in the domain. If you get the same thing out, then you started with the same thing. So this is the form of the definition that's most useful for proofs, because it's a conditional statement. The logically equivalent contrapositive is a little more intuitive, which says, given any two elements of the domain, if A1 and A2 are not the same thing, then when you put them through the function, you get out different things. So if you take different things to begin with, the function, if you plug in different numbers or whatever elements, will produce different elements in the codomain. So that's what this version says in the contrapositive. Okay, for proofs, this version up here is actually a little more convenient, okay, because you get to assume the hypothesis. If you're given something or you're trying to prove something, okay, then the hypothesis is more useful. Knowing two things are equal is a lot more information than knowing two things are not equal. If I tell you I'm thinking of two numbers and they're equal, that's extremely specific. And if I tell you I'm thinking of two numbers and they're not the same number, that could be a lot more things. Okay, so for that reason, this tends to be the definition we use in proofs, but intuitively a lot of people understand injectivity this way. And again, the two versions are just, if you got out the same thing, then you started with the same thing, versus if you start with two different things, then you get out two different things. Okay. In terms of preimages, a function is injective if and only if the preimage of every element of the codomain is either empty or a singleton, and a singleton is just a term for a set with exactly one element. Basically, If a function is injective, then no preimage can have two things in it. If the preimage had two things in it, then I could have f of two different things be equal, because I'm looking at the preimage of a single element, so I got out the same thing, but I started with two different things. So here are a couple of examples. First up, the function given by f of x equals 3x plus 1 is injective. So we need to prove that. Now remember that the definition of injectivity said, if f of x1 equals f of x2, then x1 equals x2. So we start off by assuming that f of x1 equals f of x2, and the goal is now to show that x1 equaled x2. Well, here's f of x1, here's f of x2. We can subtract 1 from both sides and then divide by 3, and we manage to show that x1 must equal x2. So anytime we assume f of x1 equals f of x2, then x1 equals x2. So we've shown the conditional statement that for any two elements of the domain, if I got out the same thing, then I must have started with the same thing. We've concluded the proof of injectivity. Second example, f of x equals 3x squared plus 1 is not injective. So let's try to think how we would prove something is not injective. Now, injectivity is a universally quantified statement. So if it fails, we just have to find one specific example where it fails, in other words, a counterexample. So if I pick these two numbers specifically, then we can begin with two numbers that are different. 4 and -4 are different numbers, but once I run them through the function, they both produce 49. So there was one example of a pair of elements of the domain that are different, but when I run them through the function, I get out the same element of the codomain. So it was not the case that every pair of elements from the domain, if they were different, then I got out different things in the codomain. So it's not injective. It was possible to get out the same element of the codomain from more than one element of the domain. Another way of phrasing this is that the preimage of the number 49 contains two different numbers, and if the preimage of any element is more than a singleton, has more than one element in it, then it's not injective. The flip side to injectivity is surjectivity. So a function with domain A and codomain B is called surjective if the following holds. Given any element of the codomain, there is something in the domain so that f of a equals b. In other words, every element of the codomain is in the range. Remember that the range is everything that the function does produce, does spit out. And this definition says everything in the codomain is actually spit out by the function. So if the codomain is actually the range, then it's called surjective. In terms of preimages, this is saying that the preimage of any element of B is not empty. That any element of B you pick has at least one element in the preimage. There is at least one element of the domain which is sent to that thing. Proving a function is surjective is a bit of a different challenge than proving it's injective. So injectivity is a universally quantified conditional statement, so you can do a direct proof of it. You assume the hypothesis, usually f of x1 equals f of x2, and then you derive the conclusion, x1 equals x2. But surjectivity is not a conditional statement, and it also has an existential quantifier in it. So how would you prove this thing? Well, we're trying to prove something about every element of B, so you start off by saying let B, little b, be an arbitrary element of the codomain. But then what you have to prove is there exists an element of the domain, which could only happen once, so you have to somehow find it. So then what you do is you have to find the particular element of the domain that is sent to that B. For simple algebraic functions, this is usually fairly straightforward, but in general, this can be quite difficult. Okay, but for any f with domain A and codomain B, you can make a related function by basically saying take the same function, fix the domain to be the same, and instead of making the codomain the entire set B, simply declare this set the range of the function to be the codomain. And now this is definitely the range of the function. The codomain and the range have been made the same. The trick is just knowing whether this set, the range of f, is actually the same as the set B or not. Okay. Proving a function is surjective is proving these two are the same set. Whatever function you have, if you simply replace the codomain with the range of f, you have automatically made it surjective, but you might not really know what this set looks like anymore. Let's take a look at an example. So here's the first one. The function given by 3x plus 1. We already showed this function was injective. Now we're going to show that it is surjective. So start with an arbitrary element of the codomain. So we have started with an arbitrary element of the codomain R, totally not specified. Now we need to find one particular element of the domain. So we can be very specific. We pick it to be whatever y was minus 1 over 3. So this was totally arbitrary because this was quantified with for any element of the codomain. Then there exists an element of the domain, so you only have to find one element of the domain, and this is the element we're going to pick, y minus 1 over 3. Then what's f of x? It's 3x plus 1, but x, recall, was y minus 1 over 3. The 3's cancel, then the 1's cancel, and we got out y. So for an arbitrary element of the codomain, we could find a single element of the domain that got mapped to it. And that's what surjectivity is. Okay, the scratch work that I haven't really shown is you say, pick any element you want in the codomain. And then our goal is to solve for which x satisfies f of x equals y. Well, this is 3x plus 1 equals y. Then I can subtract 1 and divide by 3. And get x equals y minus 1 over 3. Now that I have found a particular x that will solve this, that's the x we pick right here. However, this scratch work has no business going into your proof. It happens to be more or less duplicated here. But the way the statement is phrased, it says, for any element of the codomain, there exists an element of the domain. So pick an arbitrary element of the codomain, and then you have to declare what element of the domain is going to be picked. So you've done this work on a separate piece of paper, but now your reader just thinks you magically pulled it out of thin air. Sure, if we let x be this, then yes, f of x equals y, because you did this work beforehand. Let's take a look at another example. The function f given by 3x squared plus 1 is not surjective. On the previous slide, we showed it was not injective either. So here's a proof. We need to show that surjectivity fails. Now, surjectivity, recall, was defined as given any element of the codomain, there exists an element in the domain such that f of x equals y. If I negate this whole thing, okay, the negation changes the universal to an existential, and then it changes this existential into a universal, and then I get f of x is not equal to y. So here's what we need to show. If we pick, and there must exist at least one element of the codomain so that no matter what element of the domain we pick, f of x is not equal to y. So let's pick y equal to 0. We only have to show that this y exists, so we can be very specific about it. However, once I pick this y, now I have to let x be totally arbitrary, so let x be any real number. What we need to show is that f of x isn't equal to y. Well, f of x was not specified, okay? X was not specified, so f of x is just 3x squared plus 1. But y was specific, it was 0. Now what I know about x squared is it's bigger than or equal to 0, so f of x is bigger than or equal to 1, which means it's definitely not 0, aka not y. We found one particular element of the codomain such that for any element of the domain, f of x was not equal to y. Any f of x you could possibly compute is at least as large as 1 and therefore definitely not 0. So 0 is a specific element of the codomain that is never equal to any f of x's. Therefore, it's not surjective. There's a related notion called bijectivity. If a function is injective and surjective, we call it bijective. Okay, this is sometimes also called one-to-one. Because the function is injective, for any element of the codomain, there is no more than one element in its preimage, but because the function is surjective, there is at least one element in its preimage. So for every element of the codomain, there's at least one element because it's surjective in the preimage, and there's no more than one because it's injective. Therefore, there's exactly one element in every preimage. So let's take a look at an example. First, 3x plus 1, f of x equals 3x plus 1. We have already shown this function is injective and surjective on earlier slides, therefore it is bijective. Another example. The function in general given by f of x equals mx plus b is bijective for any choice of m and b, provided m is not 0. So let's prove it. Well, how do I prove something is bijective? Okay, we claimed this was true for any choice of m and b as long as m isn't 0. So choose any m and b, and all we know about m is that it's not 0. We need to show the function is bijective, so we need to show it's injective. Then we'll worry about surjectivity. How do you prove a function is injective? Assume f of two things spit out the same result. Well then, mx1 plus b, that's f of x1, equals mx2 plus b, that's f of x2. Cancel off the b's, and you can divide by m, and therefore x1 is equal to x2. Why was I allowed to divide by m? Because m is not 0. If m was equal to 0, I'd have 0 equals 0 here, and I can't just divide out by 0 and cancel it somehow. So it was critical that m was not 0. Now that we've shown the function is injective, let's show that it's surjective. Pick an arbitrary element of the codomain and find one specific element of the domain that is mapped to it. So for any element y in the codomain, the real numbers, pick one specific number, y minus b over m, and I'm allowed to do this computation because m is not 0. Then what's f of x? It's m times x plus b, but x was y minus b over m. The m's cancel, then the b's cancel, so f of x equals y. So for an arbitrary element of the codomain, we picked one specific element of the domain that solved f of x equals y, therefore the function is surjective. Since we've shown it's injective and surjective, that's the definition of showing the function is bijective. So any linear function whose slope is not 0 is bijective, as a function from the reals to the reals. Okay, there is a special function that we want to pay attention to called the identity function. For any set A, we can define a function whose domain and codomain are the same set A, given by the following. F of any element of A is just that element. What does the function do? Nothing. Whatever element of the set you plug in, that's what it spits out. This is called the identity function on a set. It's technically a function, it just doesn't do very much. For any set A, we claim the identity function is bijective. So we have to show it's injective. Okay. Let's assume f of a1 equals f of a2. What are we trying to derive? That a1 equals a2, but the identity function is very easy to work with. F of a1 is a1, and f of a2 is a2. So having made the assumption that plugging two things in produced the same thing, since f of a1 simply equals a1 and f of a2 simply equals a2, we get right to the conclusion. It's one line. The function is injective. Now we have to show that it's surjective. So we pick an arbitrary element of the codomain. Now we need to find a specific element of the domain that solves f of something equals a, but we already know what element to plug in there. I just put this same element of the domain into the function, and I get out the element of the codomain that we picked. So any element of the set that you pick is in the range, and therefore it's surjective. Since it's injective and surjective, it's bijective. I'll admit the identity function is not the most complicated or interesting function to look at, but it is an important one. So there's some special notation for the identity function. Depending on different sources, you either might see it written as id of x for identity, or just capital I, or this fancy double bar I. None of these are common enough that you can just automatically assume someone is familiar with it, but I have seen all of these more than once. If I am going to pick one of them to use, I would generally use this one here, but I have seen all of them, so don't get too comfortable picking one over the other. Just bear in mind, different people have different conventions. Moving on in our study of functions, permutations. Any bijection from a set to itself is called a permutation. So remember, a bijection just has to be injective and surjective. Now we're also adding on that the domain and codomain are the same set. So this is a bijection from a set to itself. That's called a permutation. Permutations essentially give you a way of rearranging a set. Replace each element of the set with where it goes under the map F. Because this is surjective, everything still shows up. Because it is injective, nothing shows up twice, so you essentially shuffle the elements around. Okay, so everything is replaced by a single element. Every element is replaced with a different element, and every element replaces something, so you move everything around. Perhaps in a different order, especially if this is a finite set. The identity function is technically a permutation, because it is a bijection whose domain and codomain are the same thing, but it's generally not going to be the only permutation. So let's look at a specific example where A is the set containing 4 elements, 1, 2, 3, 4, and I'm going to define a function very manually by saying f of 1 is 3, f of 2 is 2, f of 3 is 4, and f of 4 is 1. F is injective. Anytime I plug in different numbers, I get out different numbers. There are no duplicates here in the range. But it's also surjective because I see 1, 2, 3, and 4 all in the range. So it's injective and surjective, so it's a bijection. The domain is 1, 2, 3, 4. The codomain is the same numbers. So it's not just surjective, it's in fact a permutation. Moving right along. Suppose you have a bijection, aka injective and surjective, sometimes called one-to-one, from a set A to a set B, and we're no longer assuming these are the same set. Okay, so the domain and the codomain could be different, and since it's actually surjective, this is also the range. Then for every element of the codomain, there is a single element of the domain that is mapped to it. Okay, and again, because it's injective, there can't be more than one element in this preimage. And because it's surjective, there has to be at least one. So for a bijection, there's at least exactly one element in the preimage of every element of the range. So we're going to define a function that goes from B back to A by saying g of B is the single element of A that solves this. We know there is a solution because the function was surjective, and we know there is only one because it was injective. So whatever that one solution is, that is what you get out from the function g of B. This does define a function. Every B I plug in, there will be exactly one A. So it's a function. Everything I plug in produces one result, not more than one result. The domain is B. I can plug every B in here. Because this function was surjective, everything here has a preimage that's non-empty. So every B actually does have something corresponding to it. So it is a legitimate function whose domain is B and then produces back elements of A. So since f was a surjection, there's always at least one solution, but not two because it's injective. Therefore, it is a proper function. Okay, and it's not only is the domain all of B, but because every particular element of A corresponds to something, because I can plug it into F, g of B prime is the thing that is sent to B prime. If we already know f of A prime equals B prime, the thing that is sent to B prime is A prime. So g of B prime equals A prime. As we picked an arbitrary element of the domain, we conclude that G is surjective. I picked an arbitrary element of the codomain of G, and we found something that could be plugged into G to produce it. So G is actually surjective. Since f was a function, there is nothing in A so that f of A has two different values. In other words, G must be injective. There cannot be two different elements of B that came from the same element of A. So not only is G surjective, G is also injective. So G is a bijection that goes back from B to A, and we call this the inverse function of f. And whenever you start with a bijection, it has an inverse function, which is also a bijection. The way we write inverse functions is typically the same as we write preimages. Okay, because it's very similar, I mean, the definition involves finding preimages of things. It's not the worst of use of notation, but sometimes this notation of this superscript -1 is very specific about an inverse function, which requires the function f to be a bijection. Sometimes, however, it means preimages where f could be any function at all, and this can really vary from place to place. But let's just keep going and start talking about composition of functions. So suppose f and g are two functions. Notice that the codomain of f is the same set as the domain of g. That is important. So the range of f is actually a subset of b, and therefore a subset of the domain of g. So we can define a function with whose domain is a and whose codomain is c in the following way. Once you plug in an arbitrary element of a, what you do is first compute f of a. F of little a will be in the set b, which means I can plug it into the function g, so do that. And this is called the composition of g with f, usually notated this way. Notice that this is not a solid dot. This is not multiplication. This is an open circle for function composition. Now, in order for the composition of two functions to exist, what was really important was that the range of one has to be a subset of the domain of the other. Now, just because the composition exists one way doesn't mean it exists the other. So in this example, notice that the range of f was a subset of b, therefore a subset of the domain of g. The range of g is a subset of c, which may have nothing at all to do with the domain of f. So just because one order of composition exists doesn't mean the other one does, which is to say it's generally non-commutative. G composed with f is very different from f composed with g. Possibly one exists and the other doesn't, and even if both of them exist, they might not be the same thing. So this is really not the same thing as multiplication. Composition is very different. It might not always exist, and even if they do both exist, they might not be the same thing. So let's look at a couple examples to clarify that. First, I have a function from the reals to the integers and then a function from the integers to the naturals, where f of x is x rounded down, and g of x is x squared plus 1. So f rounds numbers down, and then g squares them and adds 1. So I can do this composition in this order because the codomain of f is the same as the domain of g. So the range of f is a subset of the domain of g. So take any real number you want and plug it into f, and then plug that into g. So that's what we're going to do over here. The composition g with f of minus pi, first plug minus pi into f, then plug that into g. So what happens when I take negative pi and I round it down? I get negative 4. And what happens when I take negative 4 and I plug it into this function? 17. So g of f of minus pi is 17. Notice that we started with a real number, and we ended up with a natural number. We can't, however, go the other way. G of minus pi, you might just think plug it in here and that's not a problem. But g was specifically given to have domain the integers. And because minus pi isn't an integer, I can't even discuss g of minus pi. Now let's talk about two functions from the reals to the reals, where f of x is 2x minus 1 and g of x is the same function we had before, x squared plus 1. So now, because the range of f is a subset of the domain of g, and the range of g is a subset of the domain of f, I can actually do both compositions, but they're going to be different things. So let's try plugging 2 into both of these. So first, f composed with g of 2 says take 2 and plug it into g, and then take that and plug it into 5. G of 2 is 5. Plug that into f, get out 9. F of g of 2 is 9. What's g of f of 2? Well, first compute f of 2. F of 2 is 3. Then compute g of 3. G of 3 is 10. So f of g of 2 was 9 and g of f of 2 was 10. Even though both orders of composition existed, they turned out to be different things. We're going to close out this video by giving some properties of function compositions. We're going to state a bunch of things, and we're not actually going to prove them all, because you should really try to do them yourself. First up, the composition of two injective functions, if it can exist, is also injective. Stated as a problem, it would look like this. Suppose f is a function with domain A and codomain B, g is a function with domain B and codomain C, and these are both injective. Then, what you need to be able to derive is that the composition g of f, which goes from A to C, is also injective. The same statement holds if you replace the word injective with surjective. So if I come back here and I say these are both surjective, then the composition must also be surjective. The composition of two bijections, if they are put together in a sensible order in a way that exists, is guaranteed to be a bijection. Now, if you've managed to do the previous two problems, this third one should come together very quickly. And similarly, if two functions are both permutations of the same set A, so not only are they bijections, but they are bijections whose domain and codomain is the same set, then you can compose them together in either order, and you will end up with another permutation of A. This makes permutations of a set kind of an interesting construction. There is always a permutation, namely the identity function is a permutation of a set. And anytime you have two permutations, you can act one on the other by function composition and get a new permutation. This gives it a really nice mathematical structure that you might study in a course called abstract algebra. Okay, moving along though, if a function is a bijection, then it has an inverse function and the composition will be the identity function. This is actually two problems in one. It says, suppose f goes from the set A to the set B and is a bijection. And therefore, f inverse, which maps B back to A, exists. Then two statements hold. I can do the following composition, f inverse composed with f. Now in this order, f goes from A to B, and then f inverse goes from B to A. So overall, we're going to start in A and end up back in A. But more specifically, it's saying that this composition is the identity function. So if I plug in something from its domain, which is just A, what I get out is not just something from A, I get out exactly what I started with. However, it's also claiming that if I do this order of composition, so now f inverse goes from B to A, and then f goes from A to B. So this order of composition starts in B and ends up back in B, and says if not only does this composition exist, but if you plug in an arbitrary element of B, you end up exactly where you started. So this altogether is the statement of this last problem.